the first question is, how does a sun affect the temperature of a planet? And really, sort of what happens is the energy from the sun will hit the planet, and that planet's going to heat up to counteract that incoming energy, basically, right? It's going to balance out the energy emitted by the planet as infrared radiation and the energy coming in as sunlight. So we know the amount of sunlight that reaches our current Earth from our current sun. It's roughly 1,361 watts per square meter, which hilariously, the website I was looking at said, to visualize this, imagine lighting a small closet with about 13 or 14 100-watt light bulbs, which, not gonna lie, doesn't tell me anything. I can't do that.
I will say this about 100-watt light bulbs, though. The fun fact I know about them is that they are the sole way that an Easy Bake Oven functions.
Oh, yeah.
Basically, the way the Easy Bake Oven was invented was that 100-watt light bulbs were just so damn inefficient that you could use the excess heat to bake cookies.
Yep. It's pretty good. So anyway, we have this amount of incoming energy. So if we take that amount of energy and we multiply it by the cross-sectional area of the Earth, because that's how much, how much of the Earth will be affected by that sunlight at a time, we wind up with 174 petawatts of energy per. Oh wait, this was per second. Wait,
petawatts. How many zeros is that?
That is 15 zeros, which is a lot. So I believe that was per second. Wait, how do I not have this number here? Hold on.
Watts is generally per second.
Watts is per second, right? Okay, that's what I thought, but I didn't have it like fully spelled out. I thought I did somewhere in my answer, but I guess I didn't. All right, so 174 petawatts of energy. So we can use that energy to figure out what the expected temperature of our planet would be. Basically, we need a couple of things. We need to know how much energy of that is reflected and how much is absorbed by the planet. To do this, we need to get the albedo, which the albedo is basically the amount of energy reflected by an object, and it's usually referring to a planet. So a completely icy or snowy planet where it's all white is going to have an albedo close to 100%, where almost all the light gets reflected. If it was completely dark, it would be close to 0%, where almost all the light is absorbed. We know Earth's albedo, it's about 31%, somewhere between, because we're definitely not, fully white, but we're not all the way dark either.
I'm trying really hard not to just hear libido.
I know.
Say albedo.
Every time I read it, I thought
now?
the exact same thing, and it's not...
How hot's the Earth getting?
Yeah. It is hilarious that there is a link between the albedo and how hot it gets, which, you're right, it's a good joke. Anyway...
You're right, it's a good joke.
It's a pretty good joke.
Add it to our podcast.
Yeah. There's a relationship between the temperature of an object and the amount of infrared radiation it's emitting, which this is the Stefan Boltzmann Law. Basically, that energy flow is a constant they came up with that's like 5.67 times 10 to the minus 8 times the temperature to the fourth power. So it scales very quickly with temperature, as you might imagine. And because of that, we can use that incoming energy, the albedo, and that constant to calculate the expected temperature of a planet, which for Earth gives us 253.6 Kelvin, which is minus 19.5 degrees Celsius or minus 3.1 degrees Fahrenheit. And you may notice a slight issue here because that is not the average temperature of our planet. Basically, this equation ignores the effects of oceans or atmosphere, just because those very much overcomplicate the calculation, because they will...
I've created an equation to tell you the temperature of the planet. It ignores a couple things, though, because it's hard.
In astronomers' defense, most planets do not have liquid water or atmospheres, and it works pretty well for them in those situations. But what I decided to do was... Well, and so the reason this happens is that atmospheres will trap in heat and act as insulation. Oceans will absorb heat and hold it better than just, base air will. So I basically took our expected temperature and the actual average temperature of the planet, which as of 2019 was about 58.17 degrees Fahrenheit or 14.85 degrees Celsius. And I used the ratio between those to get a constant that would say sort of, at least for our planet, what the effect of our atmosphere and oceans is on that temperature. So I found that our actual temperature is about 13.5% higher than the expected we get from that calculation. I just used that going forward to, correct for the atmosphere and oceans, basically. So how hot could our planet get before we're definitely going to die? So I'm going to be clear. We would die before this number because of just raw heat. But this is where life could not form anymore on Earth. Which, this is a point, it's going to actually happen in about 1.1 billion years. And what's going to happen is the average global temperature is going to hit 50 degrees Celsius, which is 120 degrees Fahrenheit. And at this point, the oceans will be so warm that they start evaporating without boiling. And once that water vapor is just in the atmosphere, the UV light from the sun will split those water molecules, and the hydrogen in them will leak out into space. And you need that hydrogen to form living cells. So that's the point where we definitely cannot have life on Earth anymore. So the question is, if we had two suns, and they were both current sun-sized, would we still be able to have life on Earth? We go through that calculation again. Having two suns just gives us twice the energy. So instead of having, 1,361 watts per square meter, it's 2,722 watts per square meter. And you work through it, and you wind up with an estimated temperature of 28.5 degrees Celsius, which adjusts to 69.3 degrees Celsius or 156 degrees Fahrenheit after doing that same atmosphere C constant. So yes, we could not have life on Earth with two current sun-sized suns. It just would not work. Conveniently, there is a way around this. So there is a link between the mass of a star and its luminosity, which its luminosity is that amount of energy coming out of it. And that link, we use it sort of in terms of our own sun, which is convenient for our purposes right here. And it's the ratio between the mass of that theoretical star and the mass of our sun, raised to the 3.5th power. So a sun twice as big as ours is going to have about 11.3 times the luminosity. A sun half as big will have about 0.088 times the luminosity. So obviously we have to thread the needle a little bit there, and it works out that if you have two suns with 82% of the mass of our sun, you wind up with about half the luminosity for each of them, and therefore the same solar energy total. So if we had two suns that were 80% of the mass of our current sun, things would be actually basically the same. One other cool thing about this, we are so close to getting orange suns instead of a yellow sun. A star's color is based on its mass, and the yellow star range is 80% the mass of our sun to 104%, so we're just short of dropping to orange suns. In spite of that, one thing we would get, the mass of a star does also determine its lifetime, which it's because the mass of a star is how much fuel it has. And you might think, oh, so a big star means it'll last a long time, but it also determines how hot it burns, and it burns through much more quickly than the extra fuel you get. So the numbers I saw, our sun has a lifetime of about 10 billion years. A sun with 75% the mass of our sun would have a lifetime of 21 billion years. So we would get some extra time, not quite all of that, but a little bit before, our sun turns into a red giant and we all die from that.
Yay.
I did see a cool thing, actually, is that apparently scientists are trying to look more, if they're looking for life on other planets, they used to always look for, yellow suns because that's what we have, and they figured that was the best bet. But they're actually starting to look more at orange suns because they're pretty close, luminosity-wise. But because they have that extra time, it gives life more time to form. So it's more likely that the conditions would be right somewhere in that billions of year time span for life to actually form. So that's kind of a cool thing I saw there. And then finally, I also looked somewhat into whether or not our suns look like Tatooines. I had that same thought. And on sheer luminosity, it's not really going to work, unfortunately. You can find like every random detail about Star Wars somewhere usually. I could not find officially what the colors of the suns of Tatooine are.
Couldn't you just take a screenshot of it and
well, the problem is the problem is there's three categories are yellow, white, and white, and that goes from 80% our sun's mass to 210% our sun's mass. Those three categories, and I can't tell exactly where they fall. As far as I can tell, one of them definitely looks red. The other one looks white, but a white star requires at least 140% of our sun's mass, and that would give like over 3 times the luminosity, which would bake us immediately. So that clearly can't be right.
We'd be a desert planet.
Right, exactly.
Tatooine.
Yeah. But no, it would like burn to a cinder. It would not actually work. I did it assuming yellow, white, and red. And you can get, if you do like the smallest yellow, white star and biggest red star, you wind up with 20% more luminosity than our current sun, which would give an average Earth temperature of like 82 degrees Fahrenheit, which is a lot higher than what we have now still. So it would technically be livable, but it would probably be a desert planet. So I'm going to say that's probably what it is on Tatooine, is a yellow, white star and a red star. And we could technically get there, but it would be pretty bad.
That was a clip from Absurd Hypotheticals, the podcast where we answer dumb hypothetical questions. For the full episode, click on the link in the description.